Hello again. This is a video on the planet interiors of our gas and ice giants. We're going to start with the planet interiors of Jupiter and Saturn, the gas giants. Jupiter and Saturn are mostly made of hydrogen and helium. We've mentioned that in the class before, but they are distinct in that way. But hydrogen and helium, these things are at super, super high pressure when you get down deep into the planet, beyond what we would kind of think of a normal atmosphere. The whole thing is atmosphere, but once we get down below a little bit, the pressures get incredibly, incredibly high. So yes, it's hydrogen and helium. Here's a little cutout of the planets, Jupiter here and Saturn. See, the hydrogen and helium are this sort of light purple color and the green. Neptune and Uranus have that a little bit, but then mostly this darker blue ice here. So Saturn and Jupiter, hydrogen and helium, but the pressures are really high, and so that does some interesting things inside the planet. Okay. With these high pressures, the gases are compressed. That's what high pressure means. The gases are compressed so much that they become liquid. So we think of hydrogen and helium as a gas, right? We fill up our balloons with helium. But at very high pressures, they change state to become liquid. And we're talking at the depths of a few thousand miles in the planet here. But there's no clear boundary. So no clear boundary between the atmosphere, the gas part, right? The atmosphere and the liquid layers. So you can think, and you might even see somewhere them people talk about the ocean on planets like Jupiter or Saturn, but it's not like going from sky to ocean like on Earth. It's a gradual change in state from gas to liquid. And of course, it's not water liquid, it is hydrogen and helium compressed liquid. Okay, so very, very high temperature pressures. And when you get to those high pressures, there's not much difference between a very dense gas and a liquid. So that's what you have kind of going on here. And of course, you have clouds too. We talked about the clouds in the last video. So at these high temperatures and pressures, you have liquid hydrogen and helium. But as you go deeper in the planet, you get even higher temperatures and pressures. So the higher pressure and temperature deeper in the planet, you get an even different kind of material. The liquid hydrogen acts like a metal, and we call that metal liquid metallic hydrogen. Okay, so at higher pressure and temperature deeper in the planet, liquid hydrogen can act like a metal called liquid metallic hydrogen. What does it mean that it acts like a metal? That means that electrons in the atom don't really stay with their own atom. They can move around freely. And that's what happens in a metal. Electrons move around freely in metals. This is why we can have electricity conducted through copper wires, for example. Here are some other cutouts. You can see here the orange is liquid metallic hydrogen. There's a lot in Jupiter, a little bit on the interior of Saturn, but you get past the gas layer and the liquid layer, and then you get this funky kind of liquid metallic hydrogen deeper in these planets. Past that, we go further down, we get to the cores. The cores of Jupiter and Saturn are likely very hot liquid still, but not hydrogen anymore. They're likely very hot liquid rock. So the same kind of things those refractory materials, right, that our terrestrial planets are made out of, silicates and carbon and those kind of things, iron, it's probably there in the center of these planets too, but very likely liquid and not solid. Besides the rock, the cores very likely have liquid waters and metals mixed in. So we get a lot of refractory materials with the rocks and the metals in the core. The outer layers are all volatiles, right? Hydrogen and helium. Let's talk about water just for a second, right? If it's really high pressure and really high temperature, why is water still liquid? It's the pressure. The pressure wins over the temperature change. Water and other things, but water is the one we're familiar with, is still liquid even at high temperatures in the center of one of these planets because the pressure is so high. There's this relationship between temperature and pressure and the state of the matter. Is it solid, liquid, or gas? And we usually think of it in terms of temperature. We get to the boiling point of water, it goes from liquid to gas. But this is well above the boiling point, but the pressure is much, much higher, so it keeps it liquid. Okay? Here's another picture for you to see what the interiors of those planets look like. There's a video about what if we tried to land on Jupiter, what it'd be like to descend through these layers of atmosphere and liquid hydrogen and liquid metallic hydrogen. So check that out. It has a good way to kind of imagine the interiors of these planets. Let's move on to the ice giants. Okay, what do the interiors of Uranus and Neptune look like? Quite a bit different than Jupiter and Saturn. These planets are denser than Saturn, but they are less dense than rock. So they're less dense than Earth, but more dense than Jupiter and Saturn. In fact, they're more dense than water. So they're sort of in this in-between place. They're not solid rock. They're not liquid water. They have a lot of elements in them that are heavier. So they have heavier, more massive elements in a smaller planet, so they are denser than Jupiter and Saturn. Remember we said Saturn could float? These guys could not. So they have a little bit of hydrogen. You can see in the figure here, they have no metallic hydrogen, but they have these ices and rock, and that's why they're a little more dense. They're made of different things than Jupiter and Saturn. There's really not much pure hydrogen or helium, especially when you get below sort of the top of the atmosphere. Not much hydrogen or helium in the lower layers below the atmosphere. The temperature and pressure are more extreme than on Earth, but not that extreme compared to Jupiter and Saturn. So the temperature and pressure are lower. Their temperature and pressure are lower than Jupiter and Saturn. So you have no liquid metallic hydrogen. Just not enough pressure to get that different state of matter, and not that much hydrogen either. It's just a different kind of interior. What do you have on the inside after you get through that atmosphere? You have deep liquid layers. Okay, I'm gonna call them ocean again, right? But remember, it's not water ocean. It's different kind of stuff. But these are slightly more like our ocean than Jupiter or Saturn, because these deep liquid ocean layers, they have dissolved gases and even salts in them. So they're a more complex substance. When we think about the liquid layers with dissolved gases and salts, what are those gases and salts? They're often kind of ices, so they're low density ices, so think kind of slushy ocean here of different things like water. There is water there. It's not all water. Methane and ammonia. We've talked about water, methane, and ammonia over and over because these molecules, these materials were very common when these planets were forming. And so in the outer solar system, these volatiles collected into these planets. So no liquid metallic hydrogen, deep liquid layers with things like methane and ammonia. That's where they get their color, primarily from the methane. They get those pretty blue and green colors. Uranus and Neptune are also interesting in that they seem to be younger than Jupiter and Saturn, like they formed later. Um, it looks like their cores, the cores of the planet, formed from small icy planetesimals. We might think of them today as comets. The leftovers from these guys forming are comets today. It took them longer to form. The disk was less dense out there, and so the planetesimals were farther apart. So you're out in the far edges of the protoplanetary disk. You have a lot of volatiles in the solid icy form. They're kind of more spread out. It's just not as dense out there in the outer disk. And so Uranus and Neptune took longer to form. So if they took longer to form, they're younger. And they formed out of different materials with more ice. So we get those inner layers that have more methane and ammonia and water ices as well. Right, one more poll for you to consider here. Just kind of going over that last point. Neptune and Uranus took longer to form because why? We just wrote it down. So quickly think about it, pause. Right. What was happening here? Stuff was farther apart. We didn't use the word denser. I said it. We wrote down that stuff was farther apart. Same idea, just different words. The protoplanetary disk was not as dense at the distance of Neptune and Uranus, the outer part, okay, the outer disk. Alrighty, that's the end of this video. See y'all another time.